If there's a tumor deep inside a brain, how do you get rid of it without damaging the healthy tissues? One way is using a procedure called gamma knife radiosurgery. What's funny about this is neither uses a knife nor is it a surgery. Instead, it uses radioactive gamma decay. But what exactly is a gamma decay? And how does it destroy a tumor without destroying the healthy tissues? And why would we use gamma decay and not alpha or beta decay? Well, let's find out. Let's start with something that we've already seen before. If you have unstable nuclei, then they will undergo an alpha or a beta decay and become more stable. Now, we've talked a lot about these in our previous videos on alpha and beta decay, so if you want more info, feel free to check that out. But what's important over here is that the daughter nuclei sometimes can be excited. What does that mean? Well, we've already heard of this before, right? When it comes to atoms and electrons, we probably already know that if you take an atom, any atom you want, with electrons around it, then the electrons can occupy different energy levels. Usually, electrons love to occupy the lowest energy level, which we call the ground state. But if you could somehow provide enough energy to it, then you could make that electron jump to a higher energy level. This is what we call excited state. Excited state basically means when the electron is in some higher energy level. Now, electrons don't like to stay in that state for a long time, and so they will quickly jump back to the ground state, and when they do that, the difference in the energy is released as a photon of light. And this is what happens in, say, LEDs, which you find in a lot of flashlights these days. When you pass current through an LED, the electrons inside of it get excited to a high energy level. And then when they de-excite, they release a photon of energy, and that's how they glow. Now guess what? Something very similar is happening over here. Turns out, just like with the case of electrons, and just like with the electrons, the protons and neutrons also have different energy levels inside the nucleus. And when the daughter nucleus is formed after an alpha or a beta decay, sometimes the protons and the neutrons can be in the higher energy levels. That's what we mean that when we say the nucleus is excited. So what's going to happen next? Well, just like with the electrons, the protons and neutrons will jump to the ground state, and when they do that, they will release a photon of light. And this photon of light is what we call gamma radiation. And this decay is what we call a gamma decay. So gamma radiation is just light, electromagnetic waves. Wait a second. This means radioactive decay gives off light. Is this why radioactive stuff is usually glowing a lot in greenish color? It makes all perfect sense, right? Oh no. These photos and the ones that you see in cartoons, they are highly misleading. Radioactive stuff doesn't glow like this. But why? It's giving off light, right? Well, to understand that, we need to look at the electromagnetic spectrum. Electromagnetic waves, because they are a wave, can have different kinds of wavelengths. If you have long wavelengths, we usually call them radio waves or microwaves, and shorter wavelengths are where we go towards ultraviolet light and X-rays. And what you can immediately see over here is that our eyes are only sensitive to a certain range of wavelength. So the question now would be, what decides the wavelength now? Well, the wavelength depends upon the energies of the photon. You may recall that light has both the wave nature and the particle nature. Photons are the particles of light. Now it turns out that if you have low energy photons, you will have longer wavelength. There's an inverse relationship between them. And if you have higher energy photons, you'll have shorter wavelength. Higher the energy, shorter the wavelength. Now if you consider the photons that you get from the electron transitions in the LEDs, then their energies lies in this region. And that's why we can see it. There will also be some photons that will lie in the infrared and the ultraviolet region, which we can't see, but a lot of them will lie in the visible region. And so the question now would be, what would be the energy of the gamma photons? Well, turns out gamma radiation, these photons have energies much higher than the energies that we get over here. And it kind of makes sense because the forces that we're dealing with over here are strong nuclear forces, which are much stronger than the electromagnetic forces that we're dealing with. So when a proton and a neutron in an excited nucleus jumps from a higher energy to a lower energy, the photon that they release will have a much higher energy compared to the photons that are released over here. So the energy of the gamma radiation is definitely higher than the visible light, higher than even the X-rays. In fact, it turns out to be the highest of all the electromagnetic waves. Gamma radiation has the highest energy photons. So clearly, it is invisible to our eyes. So even though it releases gamma radiation, which is electromagnetic waves, which is technically light, we can't see it. And so clearly, radioactive decays will not make the stuff glow. There are materials that will glow due to different reasons, but whenever they do, you can just think that, the glow, whatever you can see, is lying in the visible region, and therefore the photons must have come from the electron transitions, not from the nucleus. So just to get rid of that misconception, we'll paint these photons some other color, let's say pink. Okay, how about we take an example? So if you take, for example, cobalt-60, it's a radioactive isotope, it turns into nickel-60 via a beta decay. Now again, don't worry too much about the details of the beta decay, we've covered that in the previous video, but what's important over here is that this nickel, the daughter nucleus that you'll get, will be in the excited state. And the way we show that is we just draw an asterisk over here. And so that nickel will undergo a gamma decay. And in doing so, the nickel nucleus would have de-excited. And so immediately from this, can you see some differences between gamma decay and alpha and beta decay? Well, first of all, gamma decay will usually happen along with alpha and beta decay. It will rarely happen all by itself. That kind of makes sense, right? Because, once you have had alpha and beta decay, then the daughter nuclei would be in the excited state. And then when it de-excites, that's when you get the gamma photon. So it kind of makes sense. You would expect gamma decay to happen along with alpha and beta, but not all by itself. I mean, it can happen, but those are rare incidences. The second big difference you can see is that in an alpha or a beta decay, the isotopes change because the number of protons will change. But in a gamma decay, look, that doesn't happen. The mass number and the proton number stays put. And again, that kind of makes sense because in a gamma decay, there is nothing even spit out. There are no protons and neutrons converting into each other like what happens over here. Basically, protons and neutrons are just jumping from higher energy level to the lower energy level. So since the number of protons and neutrons, everything stays exactly the same, the nucleus also stays exactly the same. And that's why, just to denote there are no changes in the proton or the neutron number, we will put a 0 here and a 0 here as well. And the last comparison we want to make is its penetrating power. Again, we have seen before that alpha and beta radiations, they have alpha radiations, for example, they have the least penetrating power. They can be stopped by just paper. Beta, because they're slightly smaller, they can pass through paper, but you need something like aluminum or some plastic to stop it. What about gamma radiation? Well, gamma radiation has the most penetrating power. And again, we can make sense of this. If you go back to electromagnetic spectrum, we know that the visible light, for example, cannot penetrate your skin. But what about X-rays? They have higher energies, and now they can penetrate your skin, but they get bounced off by your bones. That's why X-rays are used for imaging your bones. So higher the energy, you can see its penetrating power increases. Gamma rays, they have even more energy, so they can penetrate even more. So compared to all three, gamma radiation has the highest penetration power. So if you want to stop gamma radiation, you better have few sheets of lead, for example. That's why, if you're dealing with radioactive stuff, you want to contain it properly with a lot of shielding. Usually we use lead, thick lead walls to shield it. Okay, what about its ionizing power? Well, all three radiations are ionizing radiation. This means that they can knock off electrons from the atoms, which means they can destroy tissues and cells and all of that. But of the three, gamma has the least ionizing power. Well, again, kind of makes sense because alpha radiation has +2 charge. So it's very easy for it to pull off electrons. Beta has just one positive or negative charge. So it has slightly lower. And gamma, well, they are neutral. They're photons. They are neutral. They don't carry any charge. And so they will have the least ionizing power. But they do ionize. All three are ionizing radiation. All three can cause damage to your tissue. So all three can be dangerous. All right, now we're ready to see how gamma knife radiosurgery works. We use cobalt radioisotope to produce gamma radiations. But what does that do? Well, let's go back to it. Okay, I'm gonna use my cobalt 60 to produce a narrow beam of gamma rays. Again, sorry for using the green color. Remember, it is supposed to be invisible, okay? But anyways, what's gonna happen? Well, because it has a high penetrating power, it just goes straight through. It is an ionizing radiation, but if I keep the intensity low enough, that means less number of photons over here, then it's not going to cause a lot of damage to anything. It's not going to cause any damage, let's say, which is good because we don't want the healthy tissues to be damaged, but it's also bad news because it doesn't do anything to our tumor. But what if I use a second beam that intersects right at the tumor? Now the same thing is going to happen, except we now have more photons on the tumor, which means the chances of ionization increases. This means more chances of damaging the tumor. You see where we're going with this? Let's add more beams. Let's add 100 of them. Now that tumor is going to have a hard time. It's going to get destroyed. So you see how awesome this is? Individually, the beams have low enough intensity such that as it penetrates straight through, it doesn't ionize much. But because there's so much concentration at that tumor, at that specific location, we have now a method to destroy stuff deep inside our brain without touching the healthy tissues. This is how gamma knife radiosurgery works. And you can see why we're choosing gamma radiations and not alpha or beta, because gamma has the most penetrating power. If you had used alpha or beta, they would probably get stuck somewhere in between. They also have higher ionizing power. That means more damage caused to the tissues. So gamma radiation is the best choice. I find this absolutely incredible.